Section 3.4, Group Data and Using Technology. In the previous section, I showed you how to find the mean and standard deviation for raw data, so just individual data values listed rather than grouped in a table. And now I want to show you how that is different when we do have group data. So let's jump in and look at an example, and I'll show you the differences as we move through it. The 60 mile per hour braking distances in feet for a random sample of 94 SUVs is as in the table below. So we've got these classes, 134 feet through less than 137, one car in there, and 137 through less than 147 cars in there, and so on. So we have 94 SUVs altogether. So this is a much bigger data set than we've been working in the last section with, but it doesn't seem like it so much because it has been grouped. So let's go ahead and do what they want in part A, which is to determine the mean and standard deviation for the braking distances. And the first thing we have to sort out there is what kind of mean and what kind of standard deviation are they talking about, because they didn't specify. They just said the mean and the standard deviation. But up here it says we're working with a random sample. So if this is sample data, then the type of mean we want is a sample mean. So let's start there. For x bar, we want to add up all of our data values and divide by our sample size. And so if I just started to do that, I get a little bit stuck right away. My first SUV is somewhere in the distance range from 134 feet through less than 137 feet, but it's not specified exactly how many feet it took for that SUV to stop. So what we need to do there is guess. And the best strategy for guessing when that number is in a range is to guess the midpoint. So for that one SUV, I'm going to guess right in the middle of 134 and 137, which would be 135.5. And that is going to be one of our strategies with group data. If we have a range of data, then we're going to guess the midpoint for any values that are in that class. So for the next 7 SUVs, I would continue with that idea. I don't know what those 7 are. They're somewhere between 137 and 140, so I'm going to guess right in the middle, which would be 138.5. And we'll do that for each class, and so for our X values, we're going to use midpoints. And when the class width is 3 all the way down, the difference on the midpoint should also be 3. So I'm just going to keep adding 3 to these values and fill in this column a little bit quicker. And then anytime you're filling in a column by using a pattern, it's always good to make sure that pattern held up all the way to the end. So this 156.5 should be the midpoint of 155 through less than 158, and that 156.5 is right in the middle of those two numbers. So it looks like so far so good. So let's look at the denominator of this expression. It's the sample size, and we have a sample size of 94 SUVs, so the denominator on this fraction is going to be 94. And I point that out first because I just want to remind you that if you're doing an average and you're dividing by 94, that implies that you're also adding up 94 things. So we want to look at what those 94 things are. So what's the first SUV? It's this one right here that we're guessing has a braking distance of 135.5. What's the next SUV? 138.5. And when I'm teaching this in class and I ask people what's the next one after that, they'll usually say 141.5. But that actually is not true. The next SUV is another 138.5, and then another 138.5, and another, and another, and another, and yet one more 138.5, because it says here there's 7 of them. Now it'd be kind of silly to just write it over and over again. If you're going to add the same number 7 times, then you should just say times 7. So this is a really important fact with group data. You don't just count one value from each class. You have to use the frequency to make sure that if there's 7 cars in that class, that midpoint gets counted 7 times. So when I go to the next one and it's 141.5, that's not actually the next one, it's the next 16. And then we would continue like that all the way through the table until we got to the last 2, and the last 2 SUVs have braking distances, at least we're guessing at that distance, of 156.5. And again, that would be times 2 because there's 2 cars in that class. So that's what I want to end up adding up. If I do that, because I'm multiplying by the frequency, I'll actually be adding up all 94 SUVs and dividing by 94. And if you are dividing by 94, you should be adding 94 things. So we want to go ahead and figure out what that numerator is, and we could just do that right here and write this big monstrous fraction, but what we usually do is go ahead and organize that in a table. So for each one of these sums, or each one of these terms in my sum, I want to think about what that is. So the first one is just 135.5, but you can get that by doing this x times its frequency. The frequency is 1, so you just end up with the same number. Here we had 7 SUVs that we're all considering to be 138.5. So when you add that in, there's going to be 7 of those. That's a total of 969.5. So I want to figure out what those pieces are for the next few as well. So let me go ahead and bring the calculator in. And I'm just going to continue with that pattern that you see there of multiplying the x times the f. So for the next one, the x is 141.5 times the f for that row, which is 16. So for those 16 SUVs, we're going to get a total of 2264 added to the numerator of our fraction down here. The next 29 SUVs, we're considering all of those to be 144.5, so times the 29 SUVs in that class, and that's going to contribute 4190.5 to our numerator down here. The next few have been computed already. Dropping down to the last row, we have that 156.5, and there's 2 of them in that row, so that's going to be a 313. If we were to add this column, which we're about to do, that would be equivalent to working out the numerator of this fraction. So we just go through and add all those up. 135.5, 969.5, 2264, 4190.5, 2950, and so on. So when I add all that up, I get 13,697. And that is the numerator for the mean that I'm going to compute. So I can write that in, 13,697, divide that by 94. So I can go ahead and do that on the calculator as well. And I get 145.712766. So the question does come up, how many decimal places should I put on that? So our rule in the past has always been to put at least 1 decimal more than the original data. We actually don't get to see the original data here, but in our group version we're using the midpoint to take the place of the original data. That has 1 decimal, so I'll put 2 on the mean. So my x bar is approximately 145.71. So there's the sample mean for this data. So let me go ahead and show you the formula that we use there, and also make a couple notes and a couple small adjustments to what we did above. So the first note would be that when you're using group data, you have to use the midpoint of each class for the x value of that class. So that's true anytime each class is a range. Use the midpoint to represent all the x values in that class. Because you're doing that, as soon as you start using guesses, which our midpoints are, for all those x values, our answers automatically become approximations. And so then just the adjustment that I'm going to make up above, when I found my mean, it probably would have been appropriate as soon as I plugged in those guesses to have written that as an approximately equal. So I'll go ahead and make that change. That's not super critical, but it is true. If you're guessing at your x values, you don't know the exact value. You just have an approximation. Here we have an approximate because we rounded, which is a different type of error as opposed to here where we're guessing. All right, so let's look at the formula real quick that we were using down there. For group data, normally we would say add all the x's and divide by n. But what we learned up here is that when you're adding up all the x values, it's important that you multiply by the frequency first to make sure you're actually counting all the cars. So I'll put that times f on our formula because we did do that, and that's always part of group data. So for group data, wherever you are going to add, we're now going to see a times f to make sure that we're adding all of the data values, not just one from each row. So when we go to do our sample standard deviation, if I covered up that f right there, that'd be the same formula we had in the previous section for sample standard deviation, But with group data, anytime you're going to add, first you'll multiply by the frequency. And then the same variations with the times f show up for the population values as well. So let's go ahead and give that a try for the sample standard deviation on this problem up above. All right, so we're going to use this formula right here, so let me copy that down. S is going to be the square root of the sum of the values of x minus x bar squared times the frequency divided by 1 less than the sample size. So generally, if you're doing things by hand, then wherever you see a sigma, you want to make a column in your table that has the part after the sigma, and then the sigma will be the total for that column row. So we have x minus x bar squared times f. So I want to take this part of the column and make it match that, x minus x bar squared and times f. And if I fill this in and I add it up, then that'll be the numerator for this fraction, and we'll almost be done with the standard deviation. So that's the goal here. So let's go ahead and make some headway on that. So this piece right here is going to be parentheses x. For the x, that's 141.5, minus the mean, which we just computed down here, 145.71. We'll square that and multiply it by the frequency for that row, which is 16. So sorry that didn't all fit smoothly, but we'll put it all in smoothly in the calculator, hopefully. So parentheses 141.5 minus the mean of 145.71, and the parentheses and square that, and then multiply by your frequency of 16. So we get 283.5856, and then we want to move down and do the next row. So we could type the whole thing in again, but I like to hit the second key and enter and then just make a change. The x value on that row changes to 144.5. The mean is still the same, the parentheses are still the same, the squaring's the same, but the frequency has changed. So that's now going to be 29 instead of 16. So this one is 42.4589. And then we have one more to finish off down here at the bottom. So second enter. On that last row, our x value is 156.5. The mean is still the same, but the frequency is now 2. When I have a 2-digit number there, now I want to type a 1-digit number, I'll often just do a 0 there. So I'm going to put 02. And then I have 232.8482. So I've got all the pieces, I just need the sum. So not a lot of glamour there, but we just need to go ahead and add those together. So adding all that up, I got 1715.7413. And because that is the total for this column, that is the sum of x minus x bar squared f. So that is, if we look down here, the numerator of this fraction. So s is going to be equal to the square root of 1715.7413, all divided by the sample size minus 1. We have 8 rows, but that's not our sample size. Our sample size was 94, so 94 minus 1 will be a 93 in that spot. Then I can go to the calculator. I'll clear out all that stuff, and let's work on that sum, or sorry, that square root. So the square root of 1715.7413 over 1 less than the sample size, so over 93. And I get 4.2952. Remember, our rule on rounding standard deviations is at least 5 significant figures or digits, 1, 2, 3, 4, 5, so we're good there. So that's my value of S. And so we've got our mean and standard deviation, and sample, mean, and standard deviation are x bar and S as they requested, because they said find the mean and standard deviation, but it was sample data. And again, not a huge deal, but right here, I started substituting numbers that involved guesses at my data values, so an approximate equal there is appropriate, though not necessarily vital. So that's what it looks like when you're computing the mean and standard deviation for group data. All right, let's go ahead and look at one follow-up to that now, question B. So what percentage of the data lies within 2 standard deviations of the mean? In the previous section, the way that we did that is we looked at our deviations column and just looked at how many of them were smaller than 2 times the standard deviation. But we're actually going to have some trouble doing that here because we don't have like a clean deviations column. We did the deviations, squared them, and multiplied by f all at once. So we never saw just the x minus x bar. So I'm going to have to show you a different technique than in the previous section. A lot of people actually think this technique is easier. If you want to know what percentage of the data values lie within 2 standard deviations of the mean, what we're going to do is come up with boundaries. One boundary will be the mean minus 2 times the sample standard deviation, and the other boundary will be x bar plus 2 times the sample standard deviation. So here's a mark that's 2 standard deviations to the left. This is going to be 2 standard deviations to the right. Anything that lies between the answers we get here will be within 2 standard deviations, so we'll go count them up after we do these calculations. So let's see, let's go ahead and combine those into one. X bar is 145.71, and then we're going to do plus and minus case where we do 2 times the standard deviation, which was 4.2952. And we'll break that back out into the minus case and the plus case. But they are very similar, so when I go to the calculator, I'll probably use second enter since those are so similar to each other. So let's see, 145.71 minus 2 times the standard deviation is 137.1196. And then if I just hit second enter, change that minus sign to a plus, I'll get the boundary on the other side, 154.3004. And then I want to go back up and look at the data values and decide are they in that range or not. So I want to count things that are bigger than 137.1196 but smaller than 154.3. So if you look at our chart, 135.5 is not in that range, it's too small, but 138.5 is. So this is one of our boundaries is separating right there. And then the 154.3, the other boundary, 156.5 is bigger than that, but 153.5 is smaller. So our other boundary effectively is right there. So all of these data values that lie between here and here lie within 2 standard deviations of the mean. So those are the ones that I want to count. You just have to be careful that you don't go 1, 2, 3, 4, 5, 6 out of 8, because it's actually out of 94. So it's 7 plus 16 plus 29 plus 20 plus 14 plus 5 out of 94. Now when you do things like this, a lot of times you're counting most of the data, so it can often be easier to subtract out what you don't want instead of counting what you do. So if you add all these up, you should get 91. But a faster way to do it would be to look at the total, which is 94, and say I don't want this one SUV or these two. So I'm going to write my work like this. The numerator is going to be all 94 SUVs minus the one I don't want from the top and minus the 2 that I don't want from the bottom out of 94. So that's 91 out of 94. And as a percentage, let's see what we get there. So 91 divided by 94 is 0.9681 or 96.81%. So it looks like 96.81% of these SUVs have braking distances that lie within 2 standard deviations of the mean. Alright, even though we're already finished with this problem, I want to go back through and show some shortcuts that you could use on your calculator to make this work a little bit less tedious when you're doing homework. I would point out already, as messy as all this work does look, the fact that this data was grouped saved us time, because if we had 94 pieces of raw data, we would have made a table with 94 rows in it. It wouldn't have had as many columns, but it would have had 94 rows. So this work is already speeding things up compared to just dealing with 94 pieces of raw data. But if you want to speed it up a little more, here's what you can do. Take the x values, your midpoints, and enter those into the calculator in L1. And then put the frequencies in L2. I know that's opposite of the order they're written here, but you'll see that our pattern as we go forward will be to put our x values in L1 and frequencies in L2, so I think that's a good habit. And if you enter those in, you can generate this whole column all at once. This would be L3, and what you would want to do here is take the values of x times the values of f, but where are the x's? In L1. And where are the f's? They're in L2. And if we in the calculator let L3 equal L1 times L2, it'll generate this whole column for us. We'll still have to get the sum before we can do the next column, so let me go ahead and show you this part, and then I'll show you how we could do the last piece as well. So what I'm going to want to do is go into my stat editor. So I'm going to hit stat and edit, and I'm going to enter the midpoints into L1. And then I'm going to enter the frequencies in L2. And then I'm going to type this as the column header for L3. So I'm going to arrow over, highlight the L3. Down here it says L3 equals, and that's blank. So I'm going to hit second L1 times second L2. And when I press enter, that's going to fill in all of these values. So 135.5, 969.5, and so on. You can arrow through and see all of those. And then I need the sum of that column. So if I just right arrow over and use L4 as some scratch space, then above stat we have list command. So I'll hit second and list. Go over to the math menu, down to sum, and we want the sum of the data that is in L3. So I'll hit second L3. That should give me the 13,697, and there it is. So a little bit faster than having to write all the individual numbers. And now let's go ahead and think about what we'd want to do for L4. So in L4, I want to generate this column, and so I'm just looking at this and trying to translate it into L1s, L2s, and so on. So I have open parentheses, and then I have the x values, which we have in L1, and then minus the mean, which we computed earlier, 145.71. So you're going to have to put that specific number. So that means you do have to calculate the mean from this sum before you can go to L4. And then n parentheses and square, and then times the frequencies, and the frequencies are back here in L2. And if I type that in, that'll generate all these numbers for me at once. So let me show you what that looks like. Go up to L4, hit clear. So now down here L4 is blank. What do we want it to be? Open parentheses, L1 minus the mean, which is 145.71, n parentheses, square, and times the frequencies, but those are in L2. And if I do that and press enter, it's going to generate this list for me again. If I move over a column and go to second, list, math, and sum, I can get the sum of that new column, which is 17157454. That actually is a little different than what I have down here. I think that's because I might be missing a couple digits on this one. Let's see if we can arrow over. Yeah, not sure why that ended up that way, but that should have been 104.2441, which goes to show you actually that things will be a little bit more accurate if you use this column method instead of just writing numbers down one at a time, where it's easier to make a mistake. Even if I made that mistake of forgetting those digits, that automatically is getting picked up in the calculator. So not only is this less tedious, but it can maybe even avoid some small mistakes. It turns out that that little mistake I made will not change the standard deviation. If you want to recalculate it with this new sum, you can do that, and you'll see that it still turns out to be 4.2952. But using the list editors is a way that you can speed up some of these calculations. And then I guess just since there was that one error, let's see if we can spot any more. All these had 4 decimals. Here's one that didn't. Let's go see if that one should have been something different. So that's the 64. No, that was right. So it looks like just that one spot for some reason left off a couple decimal places. But again, that doesn't end up affecting our end answer. And you can see that if you want to go back and make the changes. All right. And I want to show you how to use the statistical calculator to calculate the mean and standard deviation, both for sample or population and for both raw data and group data. So we've been looking at how to do that by hand and using tables, and even using the calculator to assist us a little bit in making the table. This is going to be different. This is looking at having the calculator essentially take over and do all the work for us. So let's look at this first example. 1 year's monthly electric bills in dollars for a family living in the southeast are as follows. Use your calculator to find the mean and standard deviation. And I'm going to pause right there for a second. When they say use the calculator to find the mean and standard deviation, we actually don't know what kind they mean. That could be sample mean and sample standard deviation, or it could be population mean and population standard deviation. So let's read on. We are only using the results to describe the year's bills. So we have all 12 months of the year, and they're only trying to describe the year's bills. So this is not a sample. We have our entire data set of interest. So I would say this is a population. So I think that's worth noting before we even get to any of the calculator stuff. This line right here implies that what we're working with is a population. And that means that when they ask us to find the mean and standard deviation, they're asking us to find the population mean mu and the population standard deviation sigma. Now typically we would do that by starting to make a table, but in this section I want to show you how we can use the calculator to get there much quicker. So all we're actually going to write down on this problem is just answers. So most of this is just something that you would watch and try and follow along. So the first thing is I want to enter that data into the calculator. So I'm going to hit the stat button. Let me go ahead and raise this up. I guess you can see that. So I'm pressing the stat button right here, and then I'm choosing the edit menu. I probably have some data in here, so I'll use the arrow keys to go up and highlight the list name. Press clear. That'll make this part empty. Down arrow accepts that, and I have a blank list. So now I'm going to just type in my data. Let me move this down so I can see the data values. 77, 81, and so on. After each value, you can either press enter or the down arrow. Either one works. One of the first checks on your data entry that you want to do is just make sure you got the right amount of data. I've finished entering my data and I'm on a blank line, and it's saying that would be the 13th value in L1 if I was to do another one. And I had 12 pieces of data, so that's a good sign. I can even arrow up and say, see, this one is the last one is the 12th value. So I've entered the right number of values, and I'll show you how to check that I don't have any typos in that as we move on to the next step. So here's where in the past we'd start finding sums and using the other columns, but what I'm going to do here is have the calculator finish off the job. And so let me move this up so you can see the buttons again. I'm going to press the stat button, and this time instead of edit, which we've been doing, I'm going to move over to calc. That's not calculus, that's calculations. It's going to make some calculations for us. We have one variable here, it's the electric bills, and we're going to choose one variable statistics because of that. So it's already highlighted, so I'm just going to press enter. And then it needs to know where the data is. I only have data in L1, but the calculator doesn't look at things like that. It kind of insists that we would tell it where our data is. So move this for a second. Above the 1 key we see the L1. So I'm going to hit second and L1 so that I'm telling the calculator I have one variable, I want statistics for that, and the data is in L1. And when I do that, I get all the answers I need. There's still a matter of decoding it, and there's also the matter of making sure I entered in the data right. When I'm asking you to do a problem using the calculator, I'll give you the sum of the x squareds, and you'll see that that's part of the output as well. We're actually not going to use that number to do any calculations, but the calculator does use it internally. I'm giving you this so you can check. If this number matches that number and you have the right number of data values, 12, then you can be confident that you've entered every value, that you don't have any typos. It is theoretically possible you could have typos and this would still match, but it's really hard to do. Very unusual that you would make a mistake and that would still match. So when you see that, you can feel confident you've entered your data correctly. Alright, so we want the mean and standard deviation. We've decided that this is population data, so we want mu and sigma. And I see sigma right here. They label it as an x, but we just put a sigma. That's in case you had multiple variables, an x and a y. You would have a sigma for your x's, a sigma for your y's. Since we don't have multiple variables, we'll just refer to it as sigma. And so that's going to be 42.214 if I go out 1, 2, 3, 4, 5 digits. And I'm going to round there, so I'm going to say approximately. So let me write that one down. I'm going to move this over a little bit. So sigma is approximately 42.214. So certainly that's a lot faster, quicker, easier than the stuff that we were doing on the previous pages where we were making the tables and doing all the individual calculations ourselves. And we want the mean as well, and you can search. There's even an arrow that says there's more stuff down, and I can scroll down, but I'm not going to find mu down there anywhere. So the calculator calculates two kinds of standard deviations, sample and population, and when we know what kind of data we have, when we determine it's population data, we pick sigma and then we write that one down. For the mean, it only calculates one kind, x bar, for the sample mean. But how does it do that? It adds up the 12 values and it divides by 12. And if we were doing a population mean, how would we do it? We would add up the 12 values and divide by 12. So even though it's not calling this mu, since this is population data, the kind of mean that applies really is mu. So they've labeled it as x bar, but we know better. We know this was population data. So we would write that down and say 106.67, and we would know that it was the mean because we know this is, or the population mean because we know this is population data. As far as the rounding rule there goes, the original data was whole numbers, so you're good at just one decimal place. But this is money, so I always feel a little strange stopping at one decimal place, which would be the nearest dime. It feels more natural to me to go out to the nearest penny. So that's it, and that would be our whole answer on that one. We've entered in our data. We chose statistics, one variable statistics, data in L1. They gave us the output. We found the two pieces we need. This one was right there for us. That one was there, but they had called it x bar, and we just had to know better and say, no, this is population data. We should refer to it as mu. And just a quick comment, they do that because it's more common for us to have a sample than a census. So it's more common for us to be computing a sample mean than a population mean. So they decided to label that as x bar because they figured that's what we would have more often. Just a quick comment, this is done with the answer, but the choices after we got all of our data in, we pressed the stat key, we went to the calculation menu, we chose one variable statistics, and then we told the calculator that our data was in L1. So that's the structure that you'd be following whenever you do your means and standard deviations on the calculator. Make sure that you're doing this work on problems that say use technology. If it says to use tables and to show your work, then you should be doing the work as we did on the previous pages. Alright, let me go ahead and show you another one. This one is an example that would work for group data. I'm going to use GPA as an example just because I think that's an interesting one for us to see in a college setting. But what I'm about to show you here is going to be for calculating the GPA. But basically what I'm going to do to make that happen is consider the units to be like the frequency on this problem. So what I'm showing you here for calculating GPA would be the same as for doing group data. It's just we're going to use the units just like we would a frequency. So let's go ahead and read the example and I'll show you how that works on the calculator. So the table below shows the number of units earned at each letter grade for a university student. Calculate the GPA for the student. So I'm going to want to enter this data in, both the number of grade points that you earn for the letter grade that you get, and then also the number of units to weight that, because if you get an A in a statistics class, which is 4 units, and you get a C in your PE class, which is typically 1 unit, those don't balance out to the B. If the stat class is 4 units, it counts 4 times as much, so we want to make sure we weight that with the units, and I'll show you how to do that on the calculator. Before we enter in the data, it's just worth noting that they listed every grade possible, A minus, B plus, B, B minus, and so on. But this student never got a C minus, so we could go ahead and just cross that line off. They never got a D plus, so we could cross that off. They never got a D minus, so we could cross that off. Sadly for them, they did get an F. We can't cross those off. We're going to have to enter them in. You could punch them in with a frequency of 0 and your answer would be fine, but since those grades never happened, it's not actually data in our data set, we could just leave it off and that'll be a little faster. Alright, so let me show you how we would do this on the calculator. I would go back into the stat menu, so I'm going to clear out this old stuff, press the stat key. We want to edit to enter in new data. We have still our bills from the problem up above, so I'll arrow up to highlight the list name, press clear and down arrow to erase that. And then for my data value, or you could say, squeeze this in, for my x's, I'm going to put the 4, the 3.7, and so on. So that's what I'm going to type in this first column. And I think if you are going to skip the ones with a frequency of 0, it's a really good idea to line them out. Otherwise, you might accidentally enter the GPA value here and then forget to do the frequency on that side, or vice versa. So if you either use them and don't cross them off and use them both, or if you're going to not use them, cross them off just to make sure you don't accidentally put them in one column and not the other. And then I'm going to go over to list 2, and what I'm going to put there are the units, and if it was some other sort of group data problem, I would put the frequencies. So I'll type those in. And just kind of note that I have the same length column. That's just a good quick check that I didn't miss anything obvious. And then again at this point, I'm going to let the calculator take over and do the rest of the work. So I'm going to hit the Stat key. I'm going to go to Calc. I'm still going to do one variable statistics. This is my variable. We never treat frequency as if it were a variable in any group data problem. I could see an argument for saying that units are a variable, but when you're computing a GPA, you treat it as a weighting value, which means it's like a frequency. So we're still going to choose one variable statistics. But we put data in both columns, so what we tell the calculator is we hit second L1 and we're saying, alright, we're doing one variable, and that's where that variable is L1. But then we need to get these frequencies used, so what we do is we hit the comma key down here, and then we use the second and the L2 option, and the calculator knows if you're doing one variable statistics that the first one is the variable and the second one are frequencies for that variable. So even though we do one variable stats, we enter two things, L1, which is our variable, comma L2, which is our frequencies. And the comma is essential. If you don't do that, it'll multiply the two together and treat it as a single variable. We really need it to see one is the variable, one is the frequency. That comma key right down here above the 7 key. So I'll press enter. And this is going to, again, do all the work for us. I would like to be able to check my work if I can. So one of the things is looking at the n. Notice it thinks we have 116 values, so somehow it is really counting these as if there were 7 times that we got a 3.7 and 24 times that we got a 3.0. And that's good. That's matching up with our total number of units. And then I'll slide this out of the way. Oh, here it is. I gave you a sum of the x squareds, so 738.96, 738.96. That's matching, so I feel good that I don't have typos. And now I want to write down my answer. So it's an interesting question whether a GPA, which stands for grade point average, is a sample mean or a population mean. Typically you're summarizing what you've done so far as a student, and so I would say you have all of your grades and you're trying to summarize them, and so I would say you're treating that as a population value. But you know, if you're transferring to another school, they're asking you for that because they're thinking of it as an estimate for what you might do in the future, so they might be looking at it as if it were sample data. It doesn't really matter that much when you're doing this computation though, because we're not going to call it mu or x bar, we're just going to call it the GPA. And it's going to be the average, and whether that's called x bar or mu, it came from adding up all the data dividing by the total number of units, which is 116. And so I'm going to say the GPA is approximately 2.31. And I'm putting 2 decimal places just because that's the standard that I'm used to seeing for GPA, so I think that makes sense. And yes, this was a 0, but followed by an 8, so we'd be rounding up there. And I think it also makes sense to do 2 decimal places here if your original data had things like 3.3, because we're supposed to put 1 decimal more on our averages than we had on the original data, so that fits there as well. And then lastly, you could ask, well, which standard deviation should I use, the S or the sigma? And I would say, well, that depends on whether you consider this to be sample data or population data. But on the other hand, it doesn't matter because we're not being asked for the standard deviation in this situation. Most of us have heard of GPA, but we haven't heard of the GPSD or something like that. So it's really not a concern on this one. But if you were doing some other type of problem, where it was group data and you had frequencies and it was sample data or population data, then just pay attention to that and pick S for sample standard deviation and sigma if it was population standard deviation. And for the mean, call it X bar if it was sample data, call it mu if it was population data. And what we did here for the GPA will apply for those other group data problems that have frequencies. And I think that's pretty much it for the calculator. Hopefully that's helpful, and you can review that as much as you need to get comfortable with those calculator computations. And I think you'll enjoy making the computation that way a lot more than making the tables, which can be pretty tedious at times.